Okay, welcome back everyone. In this video we're going to be looking at the electric force between charges, and this is known as Coulombs law. So when we have two charges, Q1 and Q2, that are separated by a distance r, well, this might look a little bit familiar. The electric force, which I'm going to write with an F and a capital E for my subscript, is equal to the product of the two charges divided by the distance squared times a constant. Well, now this is looking extremely familiar when we had two masses, m1 and m2, separated by a distance r. We had the force of gravity was a different constant times the product of the masses divided by r squared. So what we have here is another, what we call, inverse square law. So that means that the closer together the charges are, the greater the force, and it scales as 1 over r squared. So it's an inverse square. Okay, so some similarities with gravity. Well, first of all, they're both 1 over r squared laws, and they both involve two objects. So whether we're talking about masses or charges, there's two of them. And they both have a constant. So these might be our similarities between Coulomb's law, which is electric force, and Newton's law of gravitational force. Okay, so those are the similarities, but there are some very big differences. The first difference is that the constants are very different. And to illustrate this, I'll say that, remember that g is 6.67 times 10 to the negative 11th, and the units to make it work are newtons meter squared over kilogram squared. K, on the other hand, sometimes we write it with a k little e, but don't worry about that. This is the electric constant, and this is 8.99. Well, we're just going to write that as 9. 9 times 10 to the 9th Newton meter squared per Coulomb squared. So the first thing to notice is that K is about 10 to the 20th times bigger than G. And that's important. That tells us a lot about how powerful the electric force is compared to the gravitational force. We'll explore this a bit later on. Another major difference is that electric forces can repel or attract. So we talked about this in previous videos, but if I have a positive and negative charge, I will have a force of attraction, and if I have a negative and a negative, I will get repulsion. Okay? Same thing if I get a positive and a positive, I'll get repulsion. Okay? Now, how is this different from gravity? Well, gravity is only attractive. Gravity is only an attractive force. Okay? So this is a very big difference. Alright, so this is another one of those forces where you have to be able to think about, well, what happens if I change something? So since the electric force is K, Q1, Q2 over R squared, what happens if I change Q1, Q2, or R? So you have to think about each of those. And hopefully you recognize that this is exactly the same thing as GM1, M2 over r squared. And so if you increase the charge, basically F is proportional to charge. So as charge goes up, force goes up, and it's a linear thing. But if you change both of the charges, then it's not linear. Okay? And also, force is proportional to 1 over r squared. So as r goes up, the force goes down. Okay, but remember, it's an inverse square. Okay? It would probably be better to say that this is just directly proportional. Okay. Now, the last thing that I want to point out about Coulomb's law is that when we have charge, we can have positive or negative values. So if this is a plus charge, let's say it's 10 microcoulombs. And if this is a negative charge, and this is 15 microcoulombs with a negative sign, and I want to know, let's say that this is charge Q1 and this is charge Q2. Let's say I want to know the force on Q1. Well, hopefully we recognize that this would be a force going to the right, the force of 2 acting on 1. Okay? Now we have to be careful, because if we were to calculate Coulomb's law, let's not worry about K, but I would put in plus 10 for Q1 and minus 15 for Q2, and that's going to give me, let's say that they're just separated by 1 meter over 1 squared. Excuse me. Well, what's going to happen here is that I'm going to get a negative value, there's the bell again, a negative value for the electric force. And you have to be careful, because if you think about it and say, well, it's a negative value for the force, that means that it has to be going to the left, you're going to be wrong. Because if we look at our diagram, the diagram tells us that this positive charge Q1 will be attracted, or going to the right, towards Q2. Okay? Likewise, if I have a positive and a positive, okay, I'm going to get Fe, let's say that I have plus 10 and plus 15, so the only thing that would change would be the plus sign from a minus. Okay? And what happens here is I'm going to get a positive value. But clearly, what Q2 is doing to Q1 is pushing it away to the left. So the moral of the story is try to draw the force vector before you calculate the force. Okay? So draw the force vector before calculating Fe. And when you do that, you'll have a much clearer image of which way things are going. And then when you get to the end, if you notice that Fe has a negative value, that means that you have a force of attraction. And if Fe has a positive value, then that means that you have a force of repulsion. Okay? I could write that as repel. You get the idea. Okay? And this is the best way to think about it. Now, in a later video, I'm going to show an optional advanced way to think about this so that you don't have to worry about which way the force vectors are going. But that's kind of above and beyond for people who would like a bit of a challenge. Next time we'll take a look at an example problem.